I really didn't know how much time I have. He also didn't tell me the time.
Okay, so I guess we can start. Hello, everyone. Please take a seat. We're going to start now. Okay, thanks everyone for coming. Today's speaker is Metin. He's a PhD student at the Leibniz Institute for Astrophysics at Potsdam in Germany. And he came here to visit Octavio. So he's going to talk about his project he's developing right now. So go ahead.
Thank you everyone for the invitation. So I will talk about my PhD project where we used SDSS data galaxy redshift survey to reconstruct the underlying dark matter distribution and also the velocity distribution. But before I start, I would like to introduce our institute to you. Here are my collaborators and my PhD supervisor. And this is supposed to be a picture of Mexico City from the plane, but it didn't work out. So. Yeah, it's too polluted, yeah. Okay, this is the outline. Some miscellaneous talk about my institute, the motivation why I do all this, the method. It will be a little technical, the method I use. It's just the theory behind and the statistical model we use. The application to CMASS, which is a subset of Bose galaxy survey. It's a light cone. The results we get and the conclusions. Okay, let's start with the funny part. Some pictures of our institute. Our institute is located here in Potsdam. This is very close to Berlin. Many people know Berlin. Just a few people know Potsdam. Yeah, I live around here, and it takes me like 45 minutes every day to work. But the location of our institute is very nice. So let's have the history of our institute. The very beginning. So in the 17th century, our institute has its roots. It was mainly founded by some Brandenburg king to have more accurate calendars. So our institution here in the 17th century, 1711 in Berlin, it started in Berlin, was dedicated to just observe the sky to have more accurate calendars. The first achievements here, I show you precise star maps, this one, and also in the 18th century, the Neptune planet was discovered in our institute by Gottfried Galle. Here you see the Neptune, and here you see the map he used, this original map, it is still documented in our library. He used to discover the Neptune, and now you know why we have this logo. And here's the Neptune. It was predicted by something like perturbation theory for stellar orbits by an English mathematician, but he couldn't find any astronomers who would like to look into the sky where he predicted. So he was rejected by the Royal Astronomical Institute in England. So he came to Germany, and then the institutions in England were very angry that our institute found this planet and not that they did. So, yeah. So let's have a look what happened then. So after Berlin grew and grew, the light pollution grew also in the sky, so it was not possible anymore to observe the sky in Berlin itself. So what they did was to move the whole institute in 1874 to Potsdam, which was much less populated, and the sky was very bright. And this was the first building which has been established. It was dedicated. Another fact is that our institute was the first one which was only dedicated to astrophysics. So there was no institution before ours which really did only astrophysics as such. There were, of course, like universities who did like many subjects, but only astrophysics has been done in ours. And the first things which have been done were like spectroscopy of the sunlight, which you can see here. Yeah, still part of our institution here. And another funny, okay, not funny, but important fact of our institute is that the Michelson interferometry experiment has been performed in our institute too. We still have a replica of the experiment in the basement. And yeah, here Michelson tested the eta theories. Scientists didn't know how light was propagating. It was thought that there must be something like an eta, which means like air, I think, in Latin, which has to transport the light. And another theory was that light propagates through vacuum. So what he did was to split the beam into parts. One beam was going along the rotation axis of the Earth. One was perpendicular. So he knew if one beam is faster than the other, there must be an eta. If they are not, if they have the same speed, there is no eta. So that light propagates in all directions equally. And this experiment showed that the eta theory should be dismissed. And I think he also got the Nobel Prize for that, right? Does somebody know? I don't know. Okay. Yeah, if you want to see the experiment, you're welcome. It's still there. So, and after the move to Potsdam, here's our great refractor building. This is a complete dome. It has a slit and it can be opened. It was the biggest, when it was built, it was the biggest of its kind. It's still huge. And you can see the Chancellor, the Kaiser of Germany, who is visiting this refractor. Here it's in like, I am about this size. It was the last big telescope which used a lens and not a refractor, not a mirror. And you can see it was very badly damaged in the World War, so it has to be demounted completely and had to be restored, which was just recently 10 years ago, so it cost a lot. So, yeah, another thing which was discovered in our institute was the interstellar matter, which was not known before, which was done with this spectroscopical methods which have been applied in our institution. So, and this is our institution now. It's in Babelsberg, which is a part of Potsdam. Here's our lake, here's the park, and here's our institute. So this is one. You see here the main building, the other buildings, and a famous bridge. So let's have a look. This is the Leibniz building. This is newest building of our institute. This is our cosmology building and the library. It's now a library. It was also a refractor building before the World War, but it was demounted by Russians and took to Russia as a reparation because the Nazis destroyed the Ukrainian telescopes. So it's a library now. And this is the main building with the 3 domes and the MCC, called MCC. So yeah, now I walked you around around our campus. And sorry, I showed you this bridge before. For a particular reason, it is an old bridge which connects east and west parts of Germany. As you know, Germany was divided after the Second World War. And this bridge was very famous because spies have been exchanged there. Like the KGB and the CIA constantly kept exchanging spies. Did you watch the Bridge movie? Yeah, they closed all of our campus to do the movie. Yeah, actually, they also replaced the new traffic signs with the old GDR signs and really made the movie on this bridge. And here's now, this is the flag of the GDR, the East Germans, and here I think it's KGB agents. And it was really like a movie. One part started at the one end, the other at the other end. They shake hands in the middle and said, okay, see you next time. And exchanged the spies. Okay, that was it for the historical part. No. Ah, sorry, I forgot one building. This is the so-called Einstein Tower. Einstein himself proposed the experiment in 24 to measure the, to test general relativity with the sun, with sunlight, which is opened here, so the sun is getting reflected, and they tried to measure the reflection of the sunlight by when the sun is passing. Actually, this experiment failed, but the building still looks very nice. The architect is very well known. It's the architecture dynasty of Berlin, the Mendelssohn family. And it's called Einstein Tower because here's Einstein on the visiting the tower. He also lived in Potsdam for many years. Okay, I think that was it for the funny part. Now let's get to my work. So the motivation for my work is very simple. Assuming a redshift space survey, the survey infers the position of the galaxies in redshift space, which means we only measure the redshift and not the true position. The redshift, which is taken completely, consists of the Hubble flow and a so-called peculiar motion, which is unique to the galaxy itself. So this peculiar motion distorts the position in redshift space, which we call redshift space distortions. We don't know the position of the galaxy completely. We just know this part. We measure this completely, but the true position will be consisting of the peculiar motion and the Hubble flow. And what we know is that the motion of galaxies is mainly driven by the underlying dark matter and not by the mass of the galaxy itself. So it is very, very important to make a joint reconstruction of the dark matter and the velocity field to conclude the real position of a galaxy and to have a full estimate of the velocity field itself. Yeah, and this is what we're going to do. So I would first like to present the method, which is a little technical. I will present what we assume as a theoretical background, what we use as statistical model to infer. So first of all, this is an inverse sampling problem. Imagine you have a probability distribution function called f of x, which gives you, okay, the probability plotted against the random number. This would be, if I would make realizations of a probability distribution function, I would call it forward modeling. I know the probability distribution function and I just sample from it. But in our case, we have the realization and we want to conclude from that what was the real probability distribution function, which is the inverse problem. And I show you this example because we will do the exact same just in several billion dimensions. We will assume that the true underlying dark matter field is a probability density function. And what we see from it are the galaxy distributions. So what is the most probable distribution of dark matter when I see a certain population of galaxies? This is the whole problem, what we're going to solve. So, speaking in a more technical way, our goal is to create samples of this joint probability distribution function, which describes the dark matter and the radial positions of the galaxies. As input, we have the redshift space positions of the galaxies, the covariance matrix, the window function, the bias parameters, and some cosmological model. Sorry, like this. Okay, and we chunk slice this problem into two in the Gibbs sampling algorithm. We say, okay, first we reconstruct the dark matter. From the dark matter, we conclude to the velocities and correct for the positions. The corrected positions we take to reconstruct the dark matter we take to reconstruct the velocity. And Gibbs sampling says if we are able to cut our problem into conditional probabilities, we are able to sample each distribution separately by fixing the others. So we will do this chain thousands of times until we converge to a joint distribution, which is supposed to be this one. Is that clear so far? You can ask.
Curiosity, why the dark matter distribution is not depending on the cosmology?
It is by the covariance. The covariance matrix is also a function of the cosmology.
Through the covariance.
Yeah.
And the bias, what is the bias?
The bias parameters, the bias model tells you how the luminous matter follows the dark matter. This is called bias function. I will go into detail later. This is just a technical, how we write it in the paper. Okay so far? And the velocity is depending on the fiducial cosmology, the growth rate, and the content of dark matter. Okay, let's have a theoretical background how we are going to do this. So I wrote the simple equations of perturbation, what we use. Here's we use the Poisson and Euler equation and and the continuity equation to have an estimate of the linear density field evolution. This is well known from textbooks. And this is the general solution we get. So the linear perturbation are growing in position, and the time and spatial part are they're not connected anymore. They, how do you say it? They factorize. Yeah. So the evolution of time and space is factorizing. So what we will use in our model is the so-called log-normal model. We take again the continuity equation in co-moving and conformal time units. And we get this kind of solution for the continuity equation, which, as you can see, if epsilon is distributed normally, is a normal distribution, the exponential of this will be a log-normal distribution. That's why the name log-normal comes from. But we can also have a look at the Lagrangian perturbation theory, where we describe a position of a galaxy in Eulerian space as the initial conditions in Lagrangian space plus some displacement field. Okay, it's a bit technical, but we end up with this formula. So the logarithm of 1 plus delta is a good estimate of the linear distribution of the density plus some correction factor, which will, in our case, be the mean. So it looks a little complicated, but it's actually, we just need to memorize this equation. When we take the logarithm of the density field, we have a good estimate of the linear component of the field. That's all. That's what this complete calculations tell us. Questions for this so far? No? Okay, it's very clear, right? Okay, so and now the density sampling. How to estimate the density? So we use a Bayesian ansatz, where we say, okay, the posterior is a combination of the prior function, where exactly our log-normal theory comes into play, times the likelihood. So the prior tells us, okay, if I don't have any data, I assume the structure formation to evolve in a certain way. What the likelihood does is to say, okay, I have a certain amount of data. What is the probability of the density field? And to connect the density field and the number of galaxies, we have this bias function. That's it. So the likelihood connects the data to the model, and the prior is the structure formation model we put in when we don't know anything. This is bias theory. This is how we're going to reconstruct the density field. And we need a good prior because we have a lot of empty regions in the survey we are reconstructing, where we have no data and no knowledge at all. So we need a good structure formation model in order not to reconstruct any nonsense. I mean, we want the density field to look like as we would expect from nature of gravity. Okay, and this is what other groups did. They show here the logarithm of the underlying matter against the logarithm of the halo, which is a proxy of galaxies, sorry. Yeah, and as you can see in log, it's a linear function, so that it's a polynomial in not log, in natural units. That's why our Bayes model says that the number of galaxies per cell, we will discretize the problem, is proportional to the number of, to the density of dark matter to the power of alpha, where alpha is our Bayes parameter. Okay, and to solve this posterior, we use Hamilton Monte Carlo because it's a highly nonlinear and multidimensional problem. This Hamiltonian Monte Carlo says, okay, we interpret our posterior as some potential of a Hamiltonian, and what our algorithm does is to evolve the Hamiltonian with the Hamiltonian equations of motion, the Hamiltonian function. Then we use the potential of this Hamiltonian function to have an estimate of our posterior distribution. So in this way, we can avoid random walks, as, for example, the Metropolis-Hastings algorithm does, and evolve our system with clearly defined gradients. Questions to the Hamiltonian sampler? No? Okay. So the velocity sampling. The large-scale velocities is very well estimated by perturbation theory and linear approximation. It's just the gradient of the potential. So this nabla to -2 is nothing but the green function. So you actually, it would be the Laplacian of the bulk velocity would be the gradient of the density field. So we just solve it and put everything on one side. So we have a very good approximation for the large-scale velocities. And what we do with these velocities is we subtract the peculiar velocity in line of sight direction from the observed positions, so that we have a very good estimate of the real space position. Here, as I've shown you in the first slide, the total velocity we are measuring is a composition of the Hubble flow and the peculiar velocity. And in this way, we iteratively subtracting the peculiar velocity from the redshift space position. And this new position we use again to have an estimate of our density field. We reconstruct the density field and do this whole machinery ever and ever and ever again. So much theory. What is our algorithm able to perform on real data? So what we got here was the real BOSS CMASS survey and a mock survey. So the mock survey is created in a way that it's very, very close in geometry, growth, and number density to the BOSS survey. And we use the mock survey to have full control of the real space positions, because we know that all velocities, all positions in real space and redshift space, so we can test our model. We discretize our volume and run on a 6.2 megaparsec resolution volume. We take into account the survey geometry and the completeness. What is the completeness? So these are coordinates, right ascension and declination in the sky. And these points tell me, okay, our survey looked in this position photometrically, I don't know, found 3 galaxies and took the redshift of 2 of them. So the completeness in this position would be 2/3. And you can see the geometry has a lot of holes because the telescope didn't look there, or there was a bright star in the front, it has to be cut out. So the geometry is very much non-trivial to module. And what we also have is a so-called radial selection function. The farther we look, the fainter the galaxies get, the less galaxies I can take. So this has to be taken into account. So we combine the two, the mask in angular coordinates and the radial selection function in line of sight, to have a three-dimensional completeness, which I show you here in different slices. So I have a cubic box, and I cut it at different coordinates, and I plot the data below. And as you can see, the data follows the mask, of course, and we resolve the higher complete areas and the low complete areas and the totally empty areas here. So our goal is to reconstruct the complete Cartesian box. This is a mock, yeah, but the real data looks about the same. Okay, and the equations I showed you in the previous slides were valid, but only for non-evolving light cones. So we have faced several challenges when we had to analyze the light cone itself. First of all, we had to define the expectation number for galaxies per cell, lambda I, which takes also into account the growth function. So the more the different galaxies at different redshifts will have a different growth of structures. So we have to correct for that. We have different biases. We have a redshift dependent bias function here. So each galaxy has a different, according to its redshift, will have a different bias, because it will have evolved less or more according to the redshift we are taking. So galaxies which are closer to us are supposed to have more structure formation than galaxies who are far away from us. We have to take care of this, or we will have a gradient in the density field. This is what we did. And in total, our posterior looks now like this. This is the function we have to solve. Just for completeness, I showed this. Okay, and I showed you before that the logarithm of the density field is a good proxy for the linear field. This is true up to the mean field mu. This mu has different, assumes different values if I have a log-normal field or the data field. So we have to make it depending on the completeness. We didn't do this before, and we never got really good reconstructions until we did not imply this correction. And this is finally our reconstructions we get. This is smoothed over some cells. This is the complete volume we reconstruct, and this is the average over 10,000 iterations. And as you can see, the data points stay stable, where else the field where we use the log-normal field has zero mean, so it vanishes, which is exactly what we want. And here's another a little better reconstruction. Here's this cut as for the window function. This is the data, and this is the reconstruction we get. And you can see really nicely the filaments which are forming, which also where we can see the data points here. And in the area we do not know any data, our model will create a field which is consisting with the data it is taking into account. Okay, that was the, yeah. Two more things before I show the next slide. The velocities and the density. So for the density, we have the so-called pore spectrum, which is a measure for the density fluctuations. We start with a black curve. It has a bias, you can see here. This is why it's called bias. It's from the theoretical in red power spectrum. It has an offset. And this bump is due to the selection effects, because some parts are empty, some parts have not been measured very well. We correct all these effects. You can see here our reconstruction in a 2 and 1 sigma band. And you can see that we get completely unbiased results, so that the reconstruction is really, really very close to the true theoretical dark matter density field up to here percentage level accuracy. And what we show here is the quadrupole correlation function, which is a measure for the anisotropy of the data. So when you assume that you have a different velocity component in line of sight, you will assume highly anisotropic data, which is the red one. And our reconstructions show that the quadrupole is vanishing. So if you have a 0, you know that the data is totally isotropic. And you can see that our method is recovering the green curve, which is the real space mock. So we totally get rid of the anisotropies on large scales. On small scales, we still have like effects of the so-called fingers of God, which is due to the viral motion of each galaxy. We cannot correct for this one in linear theory. So you still see anisotropy on small scales, but on large scales, which we are interested in, we are completely unbiased, isotropic. Oh no. Oh no, where are the plots? The bispectrum, so I didn't have a look at it. Oh, my presentation is messed up. Oh no. Damn it. How did that happen? Sorry, give me a second. I have an older version of this talk. Maybe there we have it. What I wanted to show you is this. Here's the movie of the power spectrum, which iteration number. And you can see that we are iteratively getting closer. We have still some effects here. But as we jump from 200, I will make a jump to 10,000. Here, you can see that our chain is almost converged, and we have unbiased results here per iteration. So let me get rid of this one.
That's because you could reduce bias to only one factor, right?
Yeah, exactly. This is also gone. Sorry. Let's click here. Okay, and this is the velocity field. Here, the dark spot, the radar spots are overdensities. The blue spots are like underdensities. And as we expect, the velocity lines tend to go from voids, from underdense areas, to highly high-dense areas. So you can see immediately the gradient of what we actually expect. Yeah, I think I wanted to show more, but I don't know what happened. Sorry. Yeah. Okay. It's done already. Here's a simulation where we have here the stable density areas, and here we have random fields which are coming and going randomly. I think that's it. Let me see if I have more here. Yeah, sorry, that's it. I had 2 more slides, but my simulation is, my presentation has gone mad. So yeah, in summary, as I showed you, is we sampled the velocity and the density field simultaneously from a redshift space survey. Our reconstructions yield unbiased results for the dark matter field and also a very good estimate of the velocity field. Thanks. Sorry for this.
Questions?
what I didn't understood very well, but you get in some sense the bias. So the observed galaxy number to the dark matter,
Yes.
underlying dark matter
Yeah.
distribution. Yeah. So how is this bias? Do you
just
have the
one number.
numbers or the dependence with?
What we did was we compared the snapshot at a certain redshift of a simulation to the power spectrum we would expect. I show you. So actually, it's alpha lin. The alpha is the linear bias, and we relate this linear bias by comparing the dark matter field and the galaxy field, so that we have an estimate of the linear bias just by the ratio of the power spectra. And what we do then is, this is the linear bias in real space without evolution. So what we do is the Kaiser factor as a function of bias times growth times the nonlinear bias. So by solving this equation to alpha of z, we know exactly the function of the bias term, and we can use it for reconstructions.
And this bias, as far as I know, it depends on the type of galaxies.
Yes.
If you are red luminous galaxies
Exactly.
or blue galaxies, or so. In the case of you are analyzing BOS.
It's luminous red galaxies, exactly.
Luminous red galaxies.
Mainly luminous red galaxies. That's why it's called CMASS. It stands for constant mass. It's a survey which tries to be complete in a certain mass range. That's why we can assign only one bias parameter. If it would be different populations of galaxies, we would of course need to have a different bias.
Thanks.
More questions?
So you have a dependent of this bias on the redshift.
Yeah.
So so you said you have fixed the redshift.
No, sorry.
So have you calculated a different redshift?
Can I write somewhere? Okay. Imagine I take a snapshot at a fixed redshift and in real space and without growth function. So it's one redshift only and a complete simulation. Now I compare this one to some galaxy distribution. So I have a fixed number, right? I have just one number, which is the offset of the power spectra. But this is not, of course, only valid for one redshift. To make it dependent on a range of redshifts, I use this Kaiser factor, this Kaiser function. Kaiser function will tell me how to relate a bias in one redshift to another redshift.
Okay.
And sorry, Kaiser will tell me how to relate real space redshift to redshift space redshift. And the growth function will tell me the dependency of redshift. So I can relate a bias function in real space in one redshift to redshift space in many other redshifts.
And it's because the approximation you take is the
Yeah.
linear. So
The linear one. Alpha lin is the linear bias. And I try to make it a non-linear bias with this formula.
So I was thinking it might be bias your result in giving no.
Yeah, but it works.
More questions? No?
What exactly does the bias factor look like as a function of redshift? Is it just monotonically increasing?
No, it's not monotonically, but it's increasing with redshift.
So at higher redshift, the bias is much, much larger.
Let me think. No, it's opposite. It gets less with redshift, but it's not a linear function.
But in the local universe, the bias is almost 1. Is that
In
true?
the local universe, depending on the galaxy population we take.
Okay.
For the linear bias for luminous red galaxies at redshift 0.4, I think it's about 2.
And it would be a factor of
exactly.
10
and
larger at
no, not
No?
10. It's about 0.5 different.
at very early times.
I mean, my redshift range goes from 0.43 to 0.7, which is the
sorry. Okay.
that's
sorry,
the
I thought
redshift
this was
range
a
of
very deep-
CMASS.
Okay.
It's
All right. Thanks.
quite stable.
Galaxies are good traces of that. Let's do galaxies.
Yeah. That's very stable.
Any other question? Okay, so thanks very much again.